Hello, everyone. Hope you're doing well, and welcome to the first lecture here on an intro to classical analysis. Let's talk a little bit about what we're attempting to do here with this class. Classical analysis is arguably one of the best vehicles for proof-based learning in mathematics. The reason for this is this. Many times when we start our math majors as undergrads, we are starting with something like a calculus course dealing with how do I show derivatives and integrals and the connection between them? How can I connect this to how I draw my functions and intuitively understand continuity or differentiability to the theorems that I'm talking about, the theorems that end up being useful and helping us prove and work through these sorts of principles and theorems that we're working with. Things like the intermediate value theorem, the mean value theorem, things like this. How do I explain this to students if I am an educator in a way that makes sense to them? How can I find a way to convey the information that I know in my head in a way that's like, oh, this person, I can explain it to them and it makes sense, even though they haven't seen all of the math terms that I have, or they haven't gone through the rigorous kind of training that I've seen. This is a very good launching point for all of that to see a little bit into the why behind the mathematics, where these sorts of principles are coming from. And what's more, we're going to get to see a lot more than just at the level of calculus. We're going to be able to take some of these principles that we talked about from calculus and start extrapolating them a little bit, trying to prove them in the strongest cases possible. We're going to see that our contexts here are going to be much more general. Although they will appear more abstract, they're also going to be the same sorts of theorems that work for a larger class of spaces, more than just the real numbers, for example. You may have had at some point, and if you've taken Math 632, previously Math 689, which was a special topics course at the time in kind of intro to graduate level mathematics. This sort of course gets you an introduction into analysis on the real line. It is dealing with the real numbers in particular and showing you, yes, you can do epsilon delta proofs in this. You can connect that to proofs of the intermediate value theorem, the mean value theorem, and some of these theorems that we had seen back in our undergraduate days. But what's more, now that we have those tools in our arsenal, we can expand our results from classes like that to go for larger classes of spaces. We will be discussing metric spaces, normed spaces. We'll be discussing various function spaces and types of ways that we can be working with functions and sequences, connecting those pieces together. This is a very exciting course because of how connected it all is to the other parts of mathematics that we've seen. Now, some other people are going to argue with me on some of the points that I've mentioned, namely that this is an accessible way to see mathematics. Our friends in algebra are going to say, oh, well, this is a very interesting way of categorizing mathematics. And I very much agree. My research personally deals with a little bit of overlap from analysis and algebra. I also have a lot of interests in the world of applied mathematics, and I see a lot of applications here with what we're dealing with in our class to the world of applied math. In fact, once we get to this latter half of the course, I'm going to start trying to tie in a couple of the things that we're talking about with the historical development of where these sorts of concepts and principles, where these originated from, which was in the development of something called the Fourier series, which was a very useful way to solve a partial differential equation. And it was developed at some point in the 18th century. That's where a lot of this sort of mathematics comes from. And we'll see a little bit of those tie-ins come into the later half of this class. For now, let's get some of these principles down so that we have them solid. For the first 2 weeks, we're going to go back and see things from a proof-based perspective. We're going to go back through sets, functions, epsilon delta proofs, some of these things that we may not have seen for a while, and just start from the very beginning. Some of you may have seen this stuff already. Maybe you have taken a class like Math 645 that required you to go through and look at some of these kind of proof-based perspectives on this sort of stuff, right? Maybe you've been fluent with this in some other sort of work that you've been working on. If so, great. Hopefully these first 2 weeks are just a way for you to get to know my style of teaching, the things, the terminology and stuff that I end up finding important. You'll find the things that I stress and think, oh, okay, this is how this professor is going to be instructing. And I can think about, okay, reading the textbook in this sort of way. And we'll find ways to make connections in these first 2 weeks so that when we get into the completely new content of this course, which we'll be talking about metric spaces in week 3, we are ready to go. We're ready to move forward in that kind of perspective. But let's not dilly-dally too much here. Let's talk a little bit about what we're trying to do with this course. And the first thing I want to ask here is, what is the most fundamental mathematical truth? What is the math truth that you consider to be the most rudimentary of all of the other truths that we know for mathematics? Now, some people here are going to say 1 + 1 = 2, and or they're going to say that if you know one thing and then know that it implies this other thing, then what are the kinds of connections that you can make there? More logical connections. And I tend to fall into this latter camp. I tend to believe that the modus ponens is the deepest truth of mathematics. And here's what that is. It's the same concept as what I was describing, which is that if you know that one thing implies another, well, then if you know that the first thing holds true, then the second thing holds true as a result. It's so rudimentary as to almost be tautological, as to almost just be kind of like something very obvious. But it's a principle that governs how we develop mathematics as a whole. Although it may seem more complicated than mere letters, much of mathematics is really just this. We are saying, okay, we are in a situation in which A implies B, and we're also in a situation in which A is true. Therefore, we're going to combine these two notions and talk about how B is true. This is one of the logical truths that kind of governs the undergirding of everything that we will be talking about. We'll connect everything using modus ponens. We'll use this sort of principle several times. And I want to show you a little bit of an example in which we are using this sort of modus ponens. And that's in this propositions like this. If n squared is an even number, then so is n. Now, this is something that maybe is not quite obvious at first if you haven't seen this proposition before. N squared is an even number, so I start going through my head, okay, what are the n squareds that are even numbers? I start thinking 1 squared is 1, that doesn't work. 2 squared is 4, that does work. And take a look, 2 is an even number. Same thing with 4 squared and 6 squared and 8 squared. All of these have squareds that are even numbers. And if I think, okay, well, if I start trying to figure out if n squared is an even number, then I know, okay, starting to make some sense here that maybe the number that I'm squaring, that is also an even number. But knowing the importance of each of these words here is pertinent to our situation. If I need to sit down and prove this proposition, what are the tools that I need to make this happen? What are the ways that I could verify that this is true? I will tell you a way that I always see my freshman level students do this. Here is their understanding of a proof of this statement. They will say, note that 2 squared = 4 is even, and so is 2. And then they'll say 4 squared = 16 is even, and so is 4. And at that point, they will essentially wrap it up by saying, because we have shown this for some specific examples, I think that I have shown it for all possible examples. They use this kind of specific notion to try and make sense. They say, essentially, I believe I have established a pattern here. Now, that makes a lot of sense, and that can make some very pertinent intuition to proving some of these propositions. I'm not going to say that we don't need to be doing things like this when we're starting our proof-based process, because a lot of us as mathematicians, we're doing the exact same thing, even at the higher levels. In order to see whether or not a conjecture, something that we're not quite sure if it's true or not, if we're trying to prove or disprove a conjecture, we'll start by plugging in examples. If n squared is an even number, so we'll start with what are the squareds that are even numbers? 1, 4, 9, 16, and so on and so forth. And then we will compare back to, does this actually hold for our proposition? But there are other sorts of problems that arise from just saying, okay, for these couple of examples, these things are true, but it doesn't work for all of the examples I didn't try. Maybe there's an example out there that I missed when I was going through this quote unquote proof. So what we want is something a little bit more concrete, something that once and for all says there is no argument against this. You almost think now we are in some sort of law school environment where other people are out there saying, what if? What if you tried 6? What if you tried 8? What happens if you try these other numbers? We want to have an argument that says once and for all, this is something that always happens. This always works. And so what we are going to do is try and use something that is innate to the words themselves that we say here in this proposition, and try and connect those things together to show this proposition is true. You may already know how this sort of proposition goes, so what comes next might feel a little bit pedantic, but allow me to actually talk about the tools that we use to prove a proposition like if n squared is an even number, then so is n. What we start using are things like definitions, but it's not just definitions that we're looking for. We're looking for the right definitions. Maybe we could say this definition right here, although it works, is maybe not a good definition. It's perhaps wrong. And what I mean by wrong is that it's maybe not the right one for the context. And here is that definition. An even number is an integer ending in 0, 2, 4, 6, or 8. Notice here, by the way, this definition of even number includes the negative numbers. That is sometimes not how people think of even numbers. This also includes 0. That's not necessarily how some people consider even numbers. But in general, this is an okay definition. Mathematicians consider 0 to be even. They consider -2 to be even. So this is not a wrong definition in the sense that it is by the words incorrect. An even number is an integer ending in 0, 2, 4, 6, or 8. That works very well. But the issue is this. Now, with this definition in hand, how do I prove this proposition? N squared is an even number. It ends in 0, 2, 4, 6, or 8. How does that tell me anything about what n is? So oftentimes what we do is we look for the correct perspective in our definitions. And you'll see us do this a ton in this class. Sometimes we will define something and then we'll define it again, and then we'll define it again. We'll use all different words, all different perspectives, because sometimes when we're proving a problem, we need to be looking for the right perspective. Although multiple perspectives can exist, we want to find the one that is the easiest to manipulate using some of our mathematical operations that are pertinent in solving this problem. So this one ends up being the one that we tend to use. This definition for real is an even number n is equal to 2k for some integer k. Notice that this one, although maybe not as evocative as the definition that we gave incorrectly or the wrong one, this one is a correct definition. N is equal to 2k means that it has a factor of 2. And any factor of 2 number should be an even number. In fact, the vice versa. If something is an even number, it should have a factor of 2. It's an if and only if statement. Remember, our if and only if statements mean that if one thing is true, the other thing is true. If this other thing is true, then the one thing is also true. We go back and forth between those two statements. Now, past this point, it's maybe still a little bit tricky. What am I needing to do for this sort of definition? I have an even number n is equal to 2k. So let's see if we can use some sort of modus ponens. Let's say that we start with something that is n squared equals to 2k. Can we end up at the definition of proving that, well, n is also equal to 2k? That is kind of our direct proof of something like this. That after this point, we could use modus ponens to say this proposition works. If n squared is an even number, then so is n. But looking at this n squared equaling 2k, I would then like to say something about the nature of n. Well, if I try and maybe say, okay, n squared is equal to 2n here, or 2k. And if I want to say something about the nature of n, the mathematics here seems to want to tell me to take the square root of 2 times k. Now, I'm running into an issue here immediately, which is that I don't even know that 2k works neatly. I know 2k is a square number, right? Because, well, 2k is equal to n squared. So the fact that this is the square root of 2k, I know that this is a whole number by the fact that 2k is n squared. However, that doesn't seem to tell me much about whether or not n is even or odd. The only thing that I know is that square root of 2k is an integer. So I seem to be struggling a little bit more here and trying to figure out, okay, well, what do I do here with k? I know 2k is even, but if 2k is even and I take its square root, do I still get an even number? Again, I seem to want to go back to my examples of like, okay, it's square root of 4, square root of 16. Those seem all to work very well, but maybe there's an example that I'm not looking at too neatly here. I also start thinking, what if k is negative? Is that even possible in this scenario? And I have to start taking a look in those directions. Well, maybe there's another way that we can take a look at this, and you may have scrolled down the screen and seen that we have been looking at the contrapositive statement here for later on. Remember that the way contrapositive statements work is that we say, instead of proving the statement, if n squared is an even number, then n is an even number, we attempt to prove the contrapositive statement. Think of it this way. Let's say that we have two statements. P and Q. And let's say that P is the statement n squared is even. And that Q is the statement, well, n is even. Then what we're attempting to do here is we're trying to show that P implies Q. That if n squared is even, then n is even. Well, the equivalent statement here is that we could also be trying to show that not Q implies not P. What is this statement? This one says that if n is not even, by the way, this symbol here is meant to signify not in this statement. If n is not even, then actually n squared is not even. Are these two statements equivalent? We'll kind of think about it through this a little bit here. There's actually a little bit of logical arguing in kind of the math logic sphere as to whether these two statements are the same. But we could draw up what are known as truth tables to see that these two things have the same true and false outcomes. If P is true and Q is false, then P implies Q is a false statement because I have something that P is true and Q is something that is false. Every other instance of when P and Q could be true or false allows us to say that P implies Q is a true statement in those cases. And not Q implies not P gives us the exact same truth table. So we tend to say, okay, these are the two same statements. And indeed, in our real world, these two are the same statements. If it is cloudy outside, then it is dark. Well, if it's not dark, then it's not cloudy. That seems to make a lot of sense here. If it's cloudy, then it's dark. Seems to be a good statement. And then if we say if it is not dark, it is not cloudy, seems to be something that kind of follows directly from that when we think of how those connections are made. So that is exactly where this contrapositive statement is coming from. We say that statement, not Q implies not P, is the contrapositive statement. If n is not an even number, then n squared is not an even number. That's negating each of the two parts of this statement and also flipping their order in the implication. But now we seem up an even worse creek, which is this. Well, let's see if I can find it here. There we are. The worst creek is this. If now we show that n is not an even number, well, then n squared is not an even number. It seems like all we know now is that n is not equal to 2k for any integer k. Now that seems rough. We now say, okay, well, what is n then? If it's not equal to 2k, what are its options? You see here, I kind of sometimes write in my slideshow something that's maybe a little bit of small font, just kind of as a little bit of an aside. This might be something that you think about, like you might have thought n is not equal to 2k. Oh, okay, so is n even an integer, right? But notice that the way our proposition is written kind of implies that we're working with integers here. So we're going to read between the lines a little bit and say that it is an integer. But once we think about that n is an integer that is not even, well, then there's only one other case, which is that n is odd. And that's exactly where we get to the way that we write the proposition in a way that's a bit more useful. If n is an odd number, then n squared is also an odd number. Once we get a definition that makes sense for odd numbers, which is that n is equal to 2k plus 1 for some integer k, we now have something that allows us to mathematically manipulate what's going on here. And we can finally start making a proof. Notice that we had to do a lot of perspective shifting in order to get to this point. There are a lot of fine, but not the best perspectives to coming toward this problem. And the goal of this class is that we're going to be looking at multiple different perspectives so that after building some intuition, you will be able to find the best perspective to be viewing a problem from in order to get to a solution in the most coherent way that you can. So here we are. Here's what that proof might look like. Now we get to start with n being an odd number. Notice the advantage here is that I get to say something about n and then I want to conclude something about n squared. Let's assume that n is equal to 2k plus 1. That is that n is an odd number. Then when I go through and square it, I have 2k plus 1, a binomial that I would like to square. Well, that's going to be using some sort of distributive property. I can write all out what that is. That's 2k plus 1 times 2k plus 1, which gives me 4k squared plus 4k plus 1, which I can write as 2 times an integer plus 1 after some regrouping. That is odd by our definition. Notice we get to go backwards with our definition of odd because it's an equivalent statement to say something is odd as it is to say that n is equal to 2k plus 1. Here, I don't have k on the inside, and that's okay. What I'm really trying to signify in that definition is that n equals 2k plus 1 for any integer k. And I think that we can agree that 2k squared plus 2k is an integer. So because this is 2 times an integer plus 1, this is an odd number. Now, this may all have seemed very pedantic, and you may have known or seen some of this stuff later on or figured out what we needed to do 5 minutes ago. But what I want to show is how incredibly complicated the simple matter of even and odd numbers is. Like this was just to show if something is odd, something else is odd, or something is even and something else is even. That's all we needed to do with this problem. So imagine what it's going to look like if we need to show something with a little bit more machinery behind it. What we want to be doing is learn the language and skill together, developing the terminology and rigor together with the intuition and the skills that it takes to put together some of the proofs and the theorems that we'll be talking about here in this class. Let's get some more intuition by looking at other types of ways that we prove theorems, one of which is by way of contradiction. You can see here that sometimes I will abbreviate that as BWOC, or if I'm verbalizing it, I might say BWOC. The theorem square root of 2 is irrational, which again, you may have seen before. This sort of theorem is usually proven by contradiction. So other than direct proof, which is the proof of modus ponens, saying A implies B, or contrapositive, we might attempt to prove a statement by contradiction. What we're trying to do is assume the opposite of what we want to show, and then show that there is something absurd that ends up as a result of that. Now, this is usually a trickier style of proof. Notice that with our previous proof, we could start with something that is odd and then end with something that is, well, the thing I want to show is odd and the squared is odd. So I knew I could end at that point. That kind of signals our beginning and end of a proof. But for this sort of thing, it's hard to know where to end. Contradiction proofs are notoriously difficult for knowing when you've shown the contradiction. So you can see how we've maybe started this sort of proof here with a couple of interesting tips to help out. Here, the proof of showing that this square root of 2 is irrational. The reason that I might want to attempt a contradiction proof is that I have a better definition of square root of 2 being rational. If square root of 2 is rational, then I know it's a ratio. I know that I can write it as a ratio of integers, p over q, where, and this is important, p and q can be assumed to have no common factors. That ends up being where we end up finding our contradiction. Namely, if p and q were both divisible by 2, I could divide out by 2 and pick two numbers that don't have that common factor to 2. I could do this with any other factor, and after a finite amount of time, I could leave myself with two numbers that have no greatest common denominator other than 1, or have that as its greatest common denominator, I should say. So the way that we go through and proceed with this proof, it feels a little bit meandery. To say again, is to say we kind of feel like we're getting lost sometimes when we write through what this proof looks like, especially when you are a first-year logic student or getting started with this logic and sets. You look at this proof and think, I have no idea what's going on. I'm getting stuck in terms of no fractions because I think that's a good idea, and then I'm squaring things because I don't like square roots either. That seems to use the fact that p squared is even, so by our theorem on the previous slide, p is even. How is that even useful to me? It doesn't end up becoming useful until we've seen the entire argument. This is another thing that we'll sometimes see in this class, is that oftentimes we will have arguments that you need to read over after you've read over them again. It won't make sense the first time. But after you come back and realize the steps that were taken in order to get through the proof from beginning to end, you'll start recognizing, oh, that's why we mentioned that at the very beginning of this proof. Okay, that's why we end up taking this twist over here. Because as you can see, as we get down to the later parts of this, we use the fact that p is even to rewrite one of our previous equations to actually show that q is even, which should immediately spawn a red flag, because we assume for p and q to have no common factors. So that's exactly what we're attempting to do here. And our conclusion, now I ran out of room on the left column, I have to conclude on the right column, is that because p and q both have a factor of 2, that contradicts the fact that p and q were assumed to have no common factors. Notice at this point, this contradiction seems to have nothing to do with the fact of square root of 2 at all. It seems to have very little to do with the understanding of rational numbers, but it is a contradiction. It results in something absurd happening. This is a very common type of theorem that we tend to give students when we start out talking to them about what contradiction proofs are, is that it can result in something that is a contradiction that seems to have very little to do with what we started with. but we just ended up meandering around and finding something that ended up not working. It's very hard to develop intuition on problems like this, but we're going to try and do our best with it. We're going to try and find proofs by contradiction and become better at finding and locating these sorts of proofs to these theorems as we continue moving forward. Now, we've talked about direct proofs, contrapositive proofs, and contradiction proofs. Another type of proof that we're going to see a lot is the induction proof. This one may be not as common in analysis as you might see in some sort of discrete mathematics course or in some other sort of branches of math that you've gone through in your program. But this one is going to come up from here and there whenever we need to be having some sort of running variable. Maybe it's easy to show something is true in a one-dimensional case, and you can boil down the two-dimensional case to something involving the one-dimensional case. Then you can involve the three-dimensional case to the two-dimensional case, 4 into 3, so on and so forth. You can start thinking about how you can kind of stack up the dominoes a little bit. In fact, that's my favorite way of understanding induction, is that you have some sort of case that works well for n equals 1. That ends up being our base case. Then you know that whenever I have n equals 1 works, then n equals 2 is going to follow right after it. It's kind of like lining up the domino so that n equals 2 gets knocked down whenever n equals 1 gets knocked down. Then you can keep going for n equals 3, n equals 4, and so on and so forth. So that now that you know that the base case is true, well, the base case is true is going to knock down that first domino. So the fact that every single domino gets knocked down after that is true because of this implication that we've set up, because P of K is true, and that implies P of K plus 1. So that's exactly what we do in the theorem that says that the sum of the first n numbers can be described in a more closed form as n times n plus 1 divided by 2. Notice that we start this by writing the theorem statement for the very first case, n equals 1. This is a true statement. We can just plug in 1 and get something that's true. That seems like it's starting to do a proof by example. The thing that we said was not quite a good proof for this class. But the difference is what we do after that. We now attempt induction on the variable n. So we assume the theorem holds for some value of n equals k. Notice here the value of k is arbitrary. We have moved away from the proof by example format that we were talking about before, so that we have that something is true for n equals k case. Notice that this could have been the n equals 1 case, which would have been true. Then what we're showing in the next part is that n equals 2 would also be true. Well, then in that case, we could now go back to the beginning part of the argument after going through and showing that n equals 1 implies n equals 2, and just use the fact that n equals 2 implies n equals 3. The fact that we're using n equals k here allows us to do all of these steps all at once, to do it in a higher level of generality. Instead of n equals 1 implying n equals 2, I'm saying n equals k implies n equals k plus 1, right? That works regardless of where you are in the domino falling down. So the way that this works for this particular example is that we need to find a way to connect the fact that this is true for the n equals k case to the n equals k plus 1 case. So that is the goal. The goal for this sort of thing is to use the fact that n equals k to show the theorem holds for n equals k plus 1. And once we've done that, we now have something that we can work with. Notice that how this works is we take the formula that we got from the theorem holding for n equals k, and we add k plus 1 to it, do a little bit of factoring around and realize, wait, that's what the theorem would give me if I had plugged in k plus 1 instead of k. So that gives us what we're looking for in terms of this theorem. So that is the induction principle. These are the typical types of ways we would see things being proven in this class. Essentially, everything is going to be boiled down to one of these techniques. So when we come over a proof, my recommendation to you is to ascertain, did we prove that directly? Did we prove that using contrapositive, contradiction, or did we use some sort of induction? Did we combine any of these proof elements in one part? Then when you come to a problem that you want to see if it's true or not, try using some of these different techniques. You have more than one tool in your arsenal. Try using the ones that seem the most fit for what you're working through. The way that we usually see proofs introduced in these sorts of classes is in terms of sets, and we'll be using sets a ton in this class. It'll be something that is second nature to us. So we want to know these sets like the back of our hand. These are the notations that I'll be using for sets. The natural numbers are the counting numbers starting from 1. The integers are including 0 to the counting numbers as well as the negatives of the counting numbers. The rational numbers are those numbers that are just integers over integers, simply put, because the negative could be just in the numerator, not the denominator. Then the denominator could just be the set of natural numbers. The real number is a little bit trickier to define depending on your proximity to a real number or an advanced calculus course. You may have seen this as defined as a completion of a set. Even if you haven't, that's fine. Completion is going to be one of the main staples of this particular course we'll be talking about. So we're actually going to define the real numbers in a rigorous way as a part of this class. The complex numbers are the set of real numbers plus the set of real numbers times I. So here a and b could be any real number, so we're adding those together. Here I is the square root of -1. This ends up being very useful to us to look at things and understand these can be real spaces, we'll describe them as, or complex spaces. So we'll use complex numbers pretty heavily as a part of this class. Another thing you'll see a lot of is r to the n, which is the Cartesian product n times of the values of r, which the way we would write that is that you have n tuple coordinates. These coordinates, each of which are components-wise, are real numbers. So here I will sometimes use this notation, n, with the little brackets around it to say that I'm talking about the numbers 1, 2, 3, all the way up to the number n. Especially when I'm talking about products, this ends up being a useful notation. You might also find this useful shorthand when you're doing your own homeworks. I will also sometimes use colon equals to say is defined to be when that's useful in the context. For example, and throughout the rest, all of these sets, I could have said the natural numbers are defined to be the set 1, 2, 3. This is to kind of juxtapose from the fact that maybe I'm saying these two things are equal by some other sort of mathematical fact. No, there's no coincidence or facts that's underlying this sort of equality. That's just how I'm defining it. So continuing here, if we talk about how sets interact with each other, which really is what we want to do with mathematics. We want to talk about how everything that we are discussing, the objects that we're doing, are useful because they interact in neat ways with each other. For example, sets can union and intersect to make other sets. The way you do it is the union of any two sets is basically putting all of those two sets together in a bucket. Every element together in one little thing. You might have heard of sets as the plastic bag, and here you're just throwing everything into the plastic bag. Everything from the first set, everything from the second set. Now, if there are duplicates between those two sets, we typically don't try and rewrite any duplicates in a set. These little braces here imply that anything that's inside of here does not need to be duplicated. For example, the set 1, 1 is equal to the set containing just 1. So no need for duplicates. And otherwise, the union of these two sets, written in terms of the sets we've seen before, might look something like this. Might look like the integers unioned with the rational numbers that are non-negative. Think of that little u as that bucket that we've been throwing everything in, if that helps you make that connection. Graphing what this sort of thing looks like, we could start with all of the rational numbers that are greater than or equal to 0. Well, graphing the rational numbers on a number line seems to be a little bit difficult. It seems like you want to do a little bit of this action. And it seems like there's even more than I'm trying to write out here. But graphing the integers here is not too bad. So I would just put in -1, I'd put in -2 and -3 and so on and so forth all the way through here. This is the union between those two sets. Even though we have some duplicates at 0 and at 1, for example, there's no need to make a bigger point out of all of that. Those can just be included in the set one time. Now, the intersection of two sets is a little bit different. Instead of throwing everything into the bucket, we're going to look at things in the first set and things in the second set and ask, okay, anything in this first set, is it also in the second set? If yes, then put it in the intersection. If it's not in both sets, we're going to throw it out. So for example, the intersection of two sets written with this, think of this as like a fist bump. You don't fist bump somebody unless you have something in common between them. That's what you're trying to do for these two sets. You're looking for things that are in common between the integers and the non-negative rationals, in which case this would be the non-negative integers. That would be the thing that's in common between those two sets. Graphing that out, you'd have 0, 1, and 2, and you would include points 0, 1, and 2, but you would not include points -1, -2, because even though they are in one set, they're not in the set of non-negative rationals, so I cannot include them. Notice that I can also take the union of more than one set. I could write the union of finitely many sets in this way. I could say the union as I goes from 1 to n of a sub I. Another way that I could write this out if I wanted to is to say that this is A1 union A2 union ... union AN. This is the union of n sets all put together. Here, A1, A2, all the way up to AN. They might look very much like what these unions look like. They might look very much like the rationals or however other types of sets that we look at. We'll see some examples of these in the future. I could also take infinitely many sets and I could union them together. And the way that this is written is I equals 1 to infinity of a sub I. Notice that there's no a sub infinity. Like I'm not trying to include infinity here. The way that this is written out in less of a shorthand is A1 union A2 union A3 union ... The only thing that the infinity is implying here is that there is no end to the unions of the sets that we want to union. We're taking infinitely many of them. Starting from A1, we have defined maybe AN to be all of these different sets. For example, you can see here in this one right here, if I take A sub n to be the set of all rational numbers that have n in the denominator. So notice that this is what A sub n is. It's all the rational numbers that have n in the denominator. Then the union of all of these sets would be the set of all numbers, right? So AN here would be the set of all numbers that have any natural number inside of the denominator. But remember that we define the rational numbers to be those that have a natural number in the denominator. So in fact, the union of all of these sets is actually just the rational numbers. So that's one way that you can think of unions, that you're throwing in literally every single element from any set that's given here, and that it can be an infinite collection of sets. Intersections can be written in a similar way. If you're intersecting n sets, then it looks like the intersection from I equals 1 to n of a sub I, or the intersection as I goes from 1 to infinity of a sub I. For example, if we're taking the set as we had from above, well, then I'm looking for any particular numbers that could be written as something over n, regardless of the number n. Well, this ends up being just the integers, because any integer can be written as any number over n, but it's okay for us to write it as different numbers over n when we do so. So this would just be the integers for this intersection. Now, distributive laws are things that we're going to go ahead and just say are true, but we could actually go through and prove these things are true. Here are what those distributive laws look like here. Notice that what's going to happen is I'm going to say that in order to take a union of however many sets there are, here I don't actually specify if this is I goes from 1 to n or I goes from 1 to infinity, or if it's just the intersection of two sets when I'm writing these. Instead, I'm just saying this could be any arbitrary collection of sets that I'm unioning or intersecting. That is what is implied by this union or intersection sign with an I by it, where the indices are left unspecified. It's just meaning it doesn't really matter. It's not the important part of this theorem. What's important is how these other sets are interacting, how these other symbols are working with each other. Notice that what one says is that if you intersect B with a union of however many sets, then you could rewrite that as the union of B intersect each of those individual sets. So essentially, it is called a distributive law for sets in some way, because you're distributing out the B to each of the individual sets. And writing this in terms of how this would look in terms of just two sets, this would say B intersect A1 union A2 is equal to B intersect A1 union with B intersect A2. So notice here, it really does look like a distributive law, like you're distributing the B to each of the individual sets inside the parentheses. The same thing could be told similarly for unions and intersections. Notice that the symbols here and the choice of them is very pertinent. Although these are very short sentences, they are very intentional in how they are written. And we'll talk about that a lot in our theorems. Even if things look very succinct and very short, that doesn't mean that there's not a lot hidden inside of a statement like that. Notice that I've been using some of these terms already. I'll go ahead and just say that subset is something that is usually used in order to prove some of these things. To show that two sets are equal, then we will try and show that A is a subset of B, and that we will also try to show that B is a subset of A. We're going to try and show that these two sets are the same. Let's see an example of how something like this might look. Our typical goal here to show, say that, for example, something like A is a subset of B, is to say that is try and prove the following statement. If X is inside of A, then X is inside of B. Here I'm introducing another new notation this symbol here is meant to be is inside of, in terms of as a set, as an element inside of a set. X is inside of A, then X is inside of B. So our goal for showing that A is a subset of B is to say that if you have something inside of A, any element in there has to be inside of B. That is our notion of subset, is to try and prove this direct statement. But of course, just like any direct statement, you might be proving this by contrapositive or by contradiction, using any of the other techniques. For this one, we're just going to use a direct proof. So let's go ahead and show here that maybe that one is true here by showing that it is a double inclusion argument. Double inclusion being that we have inclusions going both ways for each of these equality sets. To write out what is meant here in this first set, the in parentheses and the kind of set going this direction, what I'm attempting to show here is that with the way that the problem is written, that B intersect the union of A sub I is a subset of the union of the sets B intersect AI. That's what is meant by this little bit of shorthand there. That's what this proof will talk about. On the other hand, this one will say that it's actually the other way around. That if you have the union, this sort of set, that this actually contains the set, which is the union of B intersect AI. So that is what is meant by each of these little bits of shorthand, is that the sign that is being used here in terms of the statement that is given in the theorem, that's the sign that we are using to try and show that part of the equality. You will see this a lot whenever we're trying to show that two sets are the same. Here, for example, in the proof of one, we're saying if X is inside of B intersect the union of A sub I, we're now just going to go through and explain what that means. What does it mean for X to be inside of that? Essentially, what we're doing is we're saying that the definitions of intersection and union that we said from up above are mathematically manipulable. I can now take those sorts of definitions and start working with them, teasing them out a little bit, saying, what does that definition really mean? And start connecting it in a way that makes sense to another statement, and then another statement. And finally, my final statement is going to be the one where X is actually inside of the union of B intersect AI, like I would like to be in. Well, what does it mean for X to be in this intersection? Because that's really what's happening on the outermost layer. It means that X is in B, and X is in the union of each of these AI. Well, what does that mean? X is in B is X is in B. Well, I'm not going to change much about that. I'm also going to say that X is in the union of A sub I to say that X is in at least one of the sets AI. Well, I'll call that set AJ to kind of distinguish that from the other sets AI that I'm using. Here, I is kind of like a running variable for me. It's not something that's determined. It's something that's more an indexing variable is how I'll usually call it. Whereas AJ, I might say, okay, well, I'm defining J to be the set so that X is inside of B and in that set AJ. So, well, if X is inside of B and X is inside of AJ, well, then X is inside of the intersection there. Well, if X is in one of the sets B intersect AI, in particular, it's in the set B intersect AJ, then I can just take the union of all of those sets, including the one of that index of J, and say X is inside of that union. That's exactly what I wanted to show for this implication. Then I could continue to do that, but go from the opposite direction. So take a look now at X being in the union of any arbitrary number of sets B intersect AI. Well, X is now in at least one set of the form B intersect AI. Well, what does it mean to be in one of those sets? There's going to be some index J, I'll call it again, so that the B is in the that X is in the intersection of B and A sub J. Well, then that means that X is in B and X is in A sub J. Notice now I'm going to try and use these pieces of information to try and end up with wherever I want to end up at. I'm going now and doing a superset here. So I'm starting from something on this side, and I would like to end up at something over here on this side of all of that. So let's see how I can do that. Since I know that X is in B, well, I already have that X is inside of here. I would like to show that X is inside of the union of A sub I. So I'm going to use a little trick, which is that I know that X is in A sub J. Well, then it's a little bit weaker, but it's okay for me to say that since X is in A sub J, X is in the union of all the A sub I's. Notice that I said that was a weaker statement. What I mean by that is A sub J is just one set. Being in the union means, oh, I'm in any one of these potentially millions of sets. That seems like a much bit of a weaker statement, but that's where I'm trying to go. I know now that this is the notation I want to end up with because that's the notation that is where I'm trying to end up at in this implication. So if we combine the fact that x is in B and x is in the union of A sub I, well, then x is in the intersection. So because those two things are true, we have that x is in the intersection as desired. And that is a way that we could use this distributive law. Notice that we had to get through quite a few details. Again, like we were mentioning before, verifying the truth is often pretty difficult. It involves a lot of details. It involves a lot of small things and trying to connect those small things in ways that hopefully make sense. Sometimes the ways that we go don't make a lot of sense. But one way that I think about doing this a lot is to say, okay, I'm going to start with something where x is in B and the intersection of the union of this with A sub I. And where I would like to end up with is x is inside of B, or rather, it's going to be inside of the union of B intersected with these A sub I. So typically my way of trying to prove these problems is to start by saying, what does it mean for x to be inside of here? I might even start working from the end and start trying to unpack this part of the definition. I might say, okay, well, the way that I understand this definition, and hopefully this is the right perspective, if not, I need to go back and try again, is that x is in at least one set of the form B intersect A sub I. Whereas I might be also trying to work from the beginning here, which says that x is in B and x is in one set of the A sub I. So now I'm going to try and think if there's some sort of way that I can connect these two pieces. You'll see me do this a lot. In fact, when we come into office hours, you'll see me kind of try and write this little bit of a kind of a proof diagram saying that this is where we start and that this is where we end over here. And there's a little bit of an ambivalence in how you try and connect these two pieces together. But the way that we ended up doing it was, well, if x is inside of one set of A sub I, then it's in the union of each of those sets of A sub I, right? Or it's in some sort of A sub j. If it's in B and it's in some sort of A sub j, then it's going to be in something of this form by definition of intersection. And that's going to be my piece that gets me all the way to the very end. That's something that takes a little bit of help. So use some time and look through these proofs. Anytime that I give a proof, use that as something to strengthen your intuition. My recommendation is do not skip any proof. Even when you're doing your reading of this, do not skip a single proof. Take time and read through it over and over again. What you're doing is you're building a logical muscle up here. And you're using that logical muscle to prove problems like this. But what that's going to do is it's going to help you understand how to prove problems 10 weeks down the road. And that's exactly where we would like to be for this class. Another bit of notation, by the way, is that we will sometimes write A slash B. So this is kind of a set minus. This is saying A minus the set B, but in order to kind of clarify, these aren't matrices or something like that we're talking about, we'll use this little slash to refer to any element that's in A but not in the set B. So for example, as we've seen from before, the integers, taking out the set of all n, where n is equal to 2k for some integer k, leaves us with the set of odd integers. On the other hand, I could have also referred to this as the complement of the even integers, the complement being all of the things that are not the even integers. But like we saw in our very beginning of this talk, sometimes you need to know what it is that we're actually talking about in order to understand what's not the even integers. Because I could have been talking about fractions, right? I could have been saying those are parts of what I'm discussing. But if our universe, that is the relevant place of information and the kinds of things that we're talking about, if our universe is just the integers, then the complement of the even integers is the odd integers. So this sort of notation cannot be given without some sort of understanding of what does it mean to not be an even integer. It means that it's in the universe, just not in that set. For example, if my universe had been R, then the set of all the even integers then is even. If I had taken the complement of that set, then I actually have a huge set. I'm looking at basically the set of all of everything, except maybe here at the even numbers, I have little holes at each of those spots. But I'm including everything else inside of my set. That's the set that I would be looking at if my universe is the set of all, if my universe is a set of all real numbers. So that can be a very different story. So knowing that context and that universe here is important. And oftentimes we're just reading between the lines to say what that universe is. You'll see here, for example, that in the proposition of, I'll say, is called DeMorgan's laws, that I'm saying given sets A1 and A2, but I'm putting in a universe U in very small text to say it's not really the emphasis of what we're going through here. These sets live in some sort of universe, but regardless of what that universe is, as long as it's understood, we can move forward with that. Then the following things are true. That the complement of the union is the intersection of the complements, and that the complement of the intersection is the union of the complements. So this is what DeMorgan's laws are saying, and you can kind of see how this sort of proof works here. If X is inside of the complement of the union, X is not inside that union, so it's not even one of the sets A sub I. Maybe you've seen this sort of proof before. If not, I recommend taking a look through this, because these are the sorts of propositions that we end up using in trying to show through and do things in the homeworks and going through the exercises that we'll be doing in this class. A quick note on the homeworks, by the way. Two things of what we're going through in our slides are very important for us as we go through and work on the homeworks. It's not only the proofs. We spend a lot of time in class talking about proofs, but it's also the statements. Once we've proven something, that's a state that we can use forever. Whenever I see the complement of a union of some sets, I can write that as the intersection of the complements. And I can just use that as a new perspective on a problem whenever it's useful to try and solve something that's a different problem. So we'll talk a little bit about that as we move along, is that we're using not only the proof writing and like, okay, this is how I write a proof, we're also using the statements themselves. Sometimes that's something that I will do is I will write a sheet out of all of the important theorems and all of the important perspectives that we've taken on a particular idea and kind of put it into one little bubble and call that sets, so that I know, okay, when I'm looking at sets and I know that that's something that I'm doing here for this problem, then I'm going to have this little list, this little formula sheet of all the things that I need to remember when it comes to sets. I recommend going ahead and developing something like that if you have not already thought about that, because that's something that we're going to be developing over the course of this, is a lot of new facts to be learning about, as well as a lot of new proofs and proof writing techniques that we could be using here. Let's go ahead and see if we can do some of these ourselves. Let's take a problem like this. Let's prove that A complement union B complement is equal to the set minus A intersect B. Now, there's a few different ways that we can do this. One different way is that we can do this using the understanding of double inclusion, which is going and saying that the first set is a subset of the second, and then the first set contains the second one. We could go through and do this. If we did this and got this, then that would be equal to a check mark. We would have everything that we would need. But another thing that we could do is we could start using some of these results that we've been talking about together with a definition of each of those sets. Let's see if we can use this latter idea. Let's prove this using the definitions and the propositions that we've been using. Let's prove this using DeMorgan's laws. Remember that DeMorgan's laws says, regardless of the indices that you're using, the complement of the union is the intersection of the complements of each of those sets. So let's actually use that here on this left-hand side. We see that A complement union B, that set complement is, and here's where I'm going to use DeMorgan's laws. I might actually, in my work, give a little bit of a reasoning as to why I'm putting this equal sign here. DeMorgan's laws, and this is the one that involves unions and complements. So I might even go one step further and say that this is the first one, the first part of DeMorgan's laws. So I might use this fact now because I have the complement of a union of two sets. I might write this down as the intersection of the complements. Notice that this is now the intersection of the complements of each of those two sets. Now, this doesn't look exactly like how it looked up here in DeMorgan's laws, but we're using the fact that here our indices could have been any arbitrary collection. This could have been two sets, this could have been infinitely many. In which case, when this is written in terms of two sets, it actually looks a little bit more like this. So I have to kind of use that translation and keep that in mind, is that sometimes the notation is not exactly the same as it would have been in that proposition. Now I get to use a few different ways of simplifying. Let's take a look at A complement complement. I have that set, but I think that there's a way to write it more simply. Another way that I can kind of confirm this is that I know based on the previous slide that this looks like A intersects B complement. So the only thing that I have different between where I would like to end up, which is with A intersects B complement, and where I'm at right now, which is A complement complement, is that I need to get A complement complement to look like A. But what makes sense here? Well, maybe in this equal sign, I'll put a little bit of an explanation, which is that the complement of a complement of a set is the set itself. Think of it this way. You've just double negated, right? You're saying it's not in the set. Well, then that means that it is in the set. So A intersect B complement, which we know by definition is A/B. And that's good enough for us. Oftentimes you will see me put a little box here if I'm ever trying to write out the problem. It's like, this is the proof. But whenever I'm writing it out using a pen and I'm not having to do the little LaTeX thing of having it do that, I'll put a little smiley face instead. Like, that is my way of saying I am done with the problem. I have finished and shown everything that I need to show for this. So I could have gone through and said, if X is an A complement union B complement, then it's not in this set, and then done explanations to get to A set minus B in order to do that. But this proof using DeMorgan's laws ended up being a little bit more straightforward. It was just using definitions and laws of things that we have proven before. So I recommend looking at different perspectives on these problems as you go through and check them out. Let's give one more example before we close out our first kind of introductory video here, talking about proofs and sets. And let's prove that the intersection over the set of all natural numbers, notice that this is an infinite intersection, of the set of open intervals from -1 over n to 1 over n is equal to the set 0. Now, something that this looks a little bit like Greek at first, but the thing that we can do is start taking a look at what these things look like. Well, where's -1 over n? Where's 1 over n in relation to the set 0? 0 seems to be right in the middle of the two of them. And it looks like I am taking the intersection, which we remember means all of them, and it needs to be in all of these sets for anything that is inside of this set. Well, that needs to be true for n. That needs to be true for n plus 1. 1 over n plus 1 we know is going to be a little bit closer to 0. And as we continue to allow n to range over all of the natural numbers, that means even let n go off toward infinity, it seems like we're going to be making this set smaller and smaller. Here, this problem asks us to prove that this is actually just the set containing 0, that it can't contain any other elements inside of this set. Let's see if we can do this using double inclusion. One inclusion for this is really easy, so I'm going to go ahead and get this out of the way. This is the one that says that this set contains this set. The set of the intersection of these open intervals contains the set 0. So I'm starting by saying, if X is in the set containing 0, then X is in the intersection of each of these. So I start like this. Let X be in the set 0. Well, there's only one element in this set, so X is equal to 0. Note that X is greater than any negative number and less than any positive number. That is the notion of 0. Remember that that's by definition a positive and negative. A positive number is one that's greater than 0, and a negative number is any number that is less than 0. So if X is equal to 0, it's greater than any negative number, and it is less than any positive number. In particular, -1 over n is less than 0, but is less than 1 over n for all n. In the natural numbers, of course, because here we are assuming that n is positive, so that -1 over n is a negative number, and 1 over n is a positive number. Then by definition of intersection, and if I wanted to be particular, I would say set intersection, but I'm okay to talk about intersection now, given the context. Then 0 is in the set of the intersection over all n and n of -1 over n to 1 over n. And we've gone through and now proven this with respect to one of our set inclusions. This is what that sort of thing might look like. Now that ends up being the easier direction. And you can see that a lot of these definitions come from things perhaps that we knew before. Seeing that 0 is inside of there is not too bad. What about the other way? Let's say that we want to show that this one's actually a subset. of this other one. Now, there's a few different ways to do this. One way to show that this is true, let's call this set A and B here. One way to show that A is a subset of B is to actually show something a little bit different. Instead of showing that A is a subset of B, something that sometimes is easier is to show that B complement is a subset of A complement. Notice that this kind of looks like the contrapositive a little bit, right? We switch the directions and make complements of each of the sets. Not in A implies not in B, or rather, not in B implies not in A. And that's one way very much to think about how this sort of thing works in terms of the sets. This is saying if an element is not in B, then it's not in A either. So if something is in A, it has to be in B. That's that notion of contrapositive there. So this is kind of like set contrapositive. How does this look in this case? Well, if B is our set 0, then we can start with let X not be in the set 0. So X is either, and I can start thinking about what that means here. If X is not 0, how am I going to show this that X is actually not in this intersection? Well, to show that X is not in this intersection, thanks to DeMorgan's laws, we know that that is the same thing as showing that it is in any of the complements of these sets. There we're using DeMorgan's laws to say that I can take the intersection of these sets to be the union of the individual complements here. So it's not going to be in one of these sets. That's my goal. Can I show that it's not in one of these sets? Well, so X is either positive or negative, is how I'm going to start. I'm now going to say something that usually you would need to go back and make sure you understand why this thing works. I'm going to use a phrase here called without loss of generality. Without loss of generality for me is going to mean that for the next thing that I'm about to choose, it really wouldn't have mattered if I had chosen the other thing. I could really just make a similar argument to show this. It would be kind of repeating myself logically to say that X is negative. So I'm just going to go ahead and show the case where X is positive. So without loss of generality, let X be positive is the way that I could write this. Without loss of generality, meaning I have two choices here. Whichever choice I make, I'm going to be doing a very similar argument. So that's what I'm going to say here. Without loss of generality, let's let X be a positive number. So, well, X is greater than 0, which means what? Is it possible now to take something like X being greater than 0 and make it so that it's actually inside of one of these sets? I think that's an interesting question. Well, note that X is greater than X over 2, right? So there's going to be some sort of element inside of here, something between X and X over 2 that makes this work. And this is going to be greater than 0. So the question is, can I use something like this to help me out? Well, if X is 1 over n, for example, then this is 1 over 2n. And I could start maybe trying to plug in some 2 over n's here in my denominators to try and make this work. But that seems like it's a little bit tricky because I'm assuming something about X. I'm assuming X is rational when I do that, but I'm not given that X is rational. The only thing I'm given is that X is positive. That's the only thing that I'm working with here. So I'm going to use a fact that we'll be talking about a little bit here. Note that X is greater than 0 and that the sequence 1 over n converges to 0. So here, notice I'm actually kind of repeating myself here. So I don't really need this note X is greater than 0 part anymore. Instead, I'm just going to say note that the sequence 1 over n converges to 0. Well, how is that useful? That means there exists a value of n in the natural numbers such that for n greater than n, 1 over n is actually less than x. Because here I'm choosing x to kind of be in my place of what a normal epsilon would be for a sequence. Well, if that's the case, then x is not in the set of all numbers between 1 over n to n. So x is in the union of n goes to n of -1 over n to 1 over n complements, which we know to be the complement of the intersection of these numbers. So I have to finish this out while also trying to find room for everything here. So allow me to zoom in and get this down here so we can just have it all written in. This is -1 over n to 1 over n complement right here. There we go. So using that DeMorgan's laws in the final step, I might even make a little note here that says this is DeMorgan's. Maybe I'll just write DM for us and say this is DeMorgan's laws. And now I have proven the B complement is a subset of A complement way of doing this. And that's good enough. That gets me where I want to be for this subset. So notice how these sorts of proofs can be done. There's a lot of different directions to take. If you get to a homework problem and you seem to have run out of solutions, come back to this video, look through the proof techniques that we've done. Go ahead and start, and I encourage this, to talk to other people here in the group. Use the little homework help forums that are given in the Canvas and talk to other people. This is my highest level of recommendation here as far as getting help from other people. These homework problems do not have to be done alone. You can help other people and you can get helped by other people. My main takeaway is that if you want to receive help on these problems at any point, please be helping other people. If you feel like it would be a good idea for you to receive help at any point, please be giving that help first. Do make the first step on that. That is going to allow an ecosystem to kind of thrive for us in those forums on Canvas so we can be connecting with each other in that way. But that's going to do it for me today. What we've been talking about is all the different ways of styling proofs using direct, contrapositive, contradiction, induction. We've talked about how it works with sets, the more direct way of doing it, or maybe some more indirect ways of showing some of these proofs. We've also defined many of the sets that we're going to be looking at: unions, intersections, DeMorgan's laws, distributive laws for each of these sets, and gone through a few different problems of how we can work through and use proofs in order to show things about sets. Y'all, I am ecstatic about this class. I'm very excited for the chance to get to teach this. I hope that you feel challenged at some point in this class, that you get to see the next thing, maybe something that you're already working on. You start to kind of develop the machinery you need to tackle that problem. That's what I'm really hoping for us in this class. Let's get us to that next mathematical stage of maturity so that we know a little bit more, that we grow a little bit more vocationally, wherever you're ending up wanting to take this material. My hope is that you feel stronger after this class, and especially in the stages of mathematical proof and in analysis. Thank you so much. Have a wonderful day.